Started section 3.3 last night, talking about increasing and decreasing functions, and specifically about the first derivative test. And we left off on problem number 4. So if you'll remember, the directions given to us are to find critical numbers, to find open intervals where it's increasing or decreasing, which involves taking a derivative, setting equal to 0, creating a sign chart, and then applying the first derivative test to decide if we have maxima or minima, and then graphing things to confirm. And I don't have a calculator today, so I might have to borrow someone's calculator, or I'll just sketch what I have. I'll just sketch, we'll do it that way, instead of worrying about switching between devices. So on this one, part A, to find critical points. Finding critical points means that I need to set things, I need to take derivatives and set things equal to 0 or equal to does not exist, if that happens in our function. So I've got x to the 1/3. What is the derivative of x to the 1/3?
1/3 x and negative 2/3.
Lovely. And the derivative of 1? Nothing, it's 0. Okay. So we're setting this equal to either 0 or does not exist. I know I don't always equal, or write down the does not exist part, but we've actually got one this time where it does not exist. No worries, come on in. So if I rewrite this in maybe a more familiar way, this would be 1/3 cube root of x squared. Is that okay with everyone? Algebra rewriting? Cool. So this won't equal 0, and the reason it won't equal 0 is why? What would happen? Yeah, because there's a 1 on top. In order for a fraction to equal 0, the numerator has to equal 0, and this numerator can't because it's just a constant 1. So it doesn't equal 0, that doesn't happen, but it does equal does not exist. That sounds funny. It does equal does not exist. So it has that possibility. And when will it not exist? Yeah. So this happens at x equals 0, right? So that's my only critical number, x equals 0. Okay. So I had a student, just so you know, and I make sure I wanted to record this as I did it. There's a problem in the homework in 3.3 where the critical points are only the points where it's equal to 0 and it doesn't show that does not exist. The reason that that happens is because it's an asymptote in the original function. And by definition, our critical points have to be places where the function exists already. So this one doesn't have that feature. The x equals 0 is not an asymptote in the original function. Does everybody see that? I can equal x in the original function, so it really is a critical point. But if you end up in any that does not exist locations that show up on the sign chart and all of that, they aren't critical points because they're functions, they're asymptotes of the original function. So that can happen. We didn't see one happen, or I don't think that we saw one happen last time, but it does happen on at least one of the problems in your homework. All right, so that's the first thing. The second thing is to take those locations, we just have one, and to do a sign chart, okay? So as we're looking at a sign chart, we're looking at finding testing values, in this case on either side of 0. And you can pick anything that you'd like, but you might as well make it things that are easy, right? So what would be the maybe easiest numbers on either side of 0? You bet, -1 and 1. And sometimes they aren't -1 and 1, but if you look at this particular equation, they are very nice. And I'm putting them into the derivative, right? I put these values into the derivative. So looking back at the derivative, you can use any version that you like. I kind of like this one the best because it's easy to evaluate with my numbers, 1 and -1. So if I put -1 in here, -1 squared is 1. The cube root of 1 is 1. So then I still have the times 3, and I've got the 1/3 in there. I have a positive number, right? So this ends up giving me a positive. And if I put a 1 in, it also gives me a positive. Now, as you're doing that, particularly for ones that are simple enough to just eyeball it and do it, that's great. If it ends up being something more complicated, like you're trying to put values, I'm just trying to remind you from last time, trying to put values into trig functions like we did over, which one was it? Was it in this lesson? That one, number 2. You might actually be a better option to just put them into your calculator, right? I mean, especially if you're choosing values that don't have very nice trig components, on a unit circle. So you can do any of them either from knowing the values specifically like we did here on this one, or from plugging them into your calculator, but you're still using the derivative if you're plugging it in the calculator. All right, so what does this tell you in terms of increasing and decreasing? Okay, we'll get to the relative extreme in a minute. That's part C. Let's finish part B, which is finding if it's increasing and decreasing. So what do the positives tell you here? It's increasing, and we have to do 2 separate intervals because it stops increasing at 0 and then it starts back doing something else, right? So it's increasing from negative infinity to 0, where it stops briefly, and then it's increasing again from 0 to infinity. So I have 2 pieces where it's increasing, separated on that one little spot by a location where, for some reason, I have an asymptote in the derivative. We're going to look at the graph in a minute, so I'll show you why. C now talks about whether I have relative extrema. So this graph is going uphill and then uphill again. I don't know why it's dotted. I apparently did some dotted lines the last time I used my iPad. It's going uphill and uphill again. So do I have any relative extrema at 0? I do not. So there are no max or mins. Or you can simply say there's no relative extrema. And then part D actually has this graph, this thing. So you probably know what this graph basically looks like. It's a cube root of x, and then the plus 1 means it's shifted 1. So this graph actually looks something like, so it won't be a perfect picture, but I shifted up 1, we're right here, and then my graph goes something like this and something like this, more or less. So what happens then at the x value of, oh, I shifted it right 1 and up 1. My apologies. Let me shift it back. I didn't mean to do that. Okay, let's do this instead. It looks like that. Get my graph right. Okay, so at the x value of 0, what's actually happening there is something that I mentioned once upon a time, but we haven't seen an example of it, and now we do. We actually have a vertical tangent line on the y-axis. Okay, so there was actually 3 locations where derivatives didn't exist. One of them was holes in the graph, right? Jumps, the discontinuities basically, includes asymptotes. Another one was sharp points, sharp turns, right? Cusps in the graph. We've seen examples of that happening. It doesn't even always happen piecewise. It happens sometimes when funny things are squared. And then the last one is when we have locations where we have vertical tangent lines. This is a vertical tangent line. So that's why the derivative's not existing there, even though the function is perfectly, reasonably differentiable everywhere else. Any questions on that? Okay. One more. So the directions, are a little bit different on this one. It says consider the function on the interval specifically 0 to 2 pi. That makes sense because we're looking at a trig function here. It wants to find open intervals where it's increasing, decreasing. It wants us to apply the first derivative test, and it wants us to use a graphing utility to confirm. So while the directions set up slightly differently, the only real difference, even though they've labeled the A, the B, the C parts differently, is the part that it's actually confined to 0 to 2 pi, right? Everything else is actually the same. It doesn't specifically say find the critical points, but you have to do it, right? It's part of part A. So it's sort of hidden in those directions. There's really still 4 parts. All right, so as we're starting part A, which will include all of the sign chart parts on this one. My derivative will be what? 1 plus 2 cosine of x. Is everybody good with that? Yes, good job. Then we're going to set it equal to 0. It's a trig function, so I'll subtract my 1. So I have 2 cosine of negative equals negative 1. I'll divide by 2, so cosine of x equals negative 1/2. And then within the unit circle, I need to find the locations where the cosine value is equal to negative 1/2. So let's start out with the negative part. Where is my cosine value negative? Which quadrants? 2. Whoa, that was the wrong tool. 2 and 3. Okay, cosine on the unit circle are the x values, and the x values are negative in quadrants 2 and 3. Excellent. Cosine values are the x values, right? So I need my x value to equal 1/2. Well, the only time I get values that are equal to 1/2 and square root of 3 over 2, actually I'll do it up here first, are either at the pi over 3s or the pi over 6s, right? Which of those two, this is some kind of an over 3 value, and this is some kind of an over 6 value. So without being super specific right now what they are, which of them gives you an x value that's going to equal 1/2?
The 12 over 3.
the top one, the one that's closest to the y-axis, right? So it's actually this location. And this location will mirror down to here as well. So I have these two angle measures. So I need to figure out what those two angle measures are that give me the correct the correct cosine value that's -1/2. So what pi over 3 values am I at in each of those locations? Does anybody know? Okay, 2 pi over 3, that's the first one. And 4 pi over 3 is the second. Good job. So if you have to count them up, you can, right? There's a pi over 3 here, and I have 2 pi over 3, the one we needed. 3 pi over 3 is always the 180 degrees. It's on the far right, far left, excuse me. I have my 4 pi over 3, and then I have 5 pi over 3 down here. So you can count around if you need to think of it that way. So I have 2 critical points, and I'm confined to the interval 0 to 2 pi. So as I make my sign chart, if you want to put the end points here as 0 and 2 pi, we'll need that in a little bit. And putting them in order, not necessarily spaced out in any way, shape, or form. These are our 2 values. So I need values in between these. Some things are easy to pick and some are not. So can you pick me an easy, and I like whole number values, that's my preference. I don't really want to use any trig radian values that are nice, I don't care. I can use my calculator. So what would be a value, numerical, just like a whole number between 0 and 2 pi that would be nice? 1 would be great. Okay, and if you aren't sure, type in your calculator 2 pi over 3. It's going to spit back out at you some kind of a decimal approximation. What does it say? I don't have mine today.
2.09.
2.09. And what does it say for 4 pi over 3?
4.18.
4.18. And then, of course, 2 pi we know is 6.28. So these are the things we're looking for between. So what's a nice value between 2.09 and 4.18? 3 would be great. 4 would be fine, too. I'll put 3. And then I need a value between 4.18 and 6.28. Either 5 or 6 would be fine. I'll use 5. Okay. Is everybody good so far? If you're choosing the values like that, your calculator is going to be what you want to do to use to evaluate them. So in your calculator, one of the easiest ways to do it is to take this derivative and to put it into y1. Okay, so in y1, I would type 1 plus 2 cosine x. That's what I would do. And I'd go into the table. And in the table, I'd put in our 3 values, 1, 3, and 5. And what I want to know is the sign. So let me give you a second to get in the calculator, those of you who have them today and are doing that. Okay, when you put the number 1 in, do you get a positive or a negative? I'm hearing positives, so that's good. Well, that matches my notes. That's even better. How about the number 3? A negative. And the number 5? A positive. And most of the time with sine and cosine kind of curves, they do in fact oscillate. Doesn't always happen, especially if things are like squared and so forth. But most of the time we see a lot of oscillation. So that seems quite reasonable. Now if I'm identifying where things are increasing, decreasing, moving from left to right, what's happening first? Close.
0 to 2.
0. Yeah, we'll start with 0. Okay, so first of all, it's increasing. Let me write that first. It's increasing. We'll start at 0, and we'll stop increasing at 2 pi thirds. And then it picks up increasing again over here in the second half, or the last third-ish, at 4 pi over 3 to 6, not 6, to 2 pi. And then in between there, it's decreasing. So it's decreasing from 2 pi over 3 to 4 pi over 3. So this is the answer, if you will, to part A, because it asks me about intervals where it's increasing, decreasing. We've taken care of that. We're looking for relative extrema now. So the relative extrema have to do with the positives and negatives on that sign chart and what they mean in terms of the graph. So positive means the graph is increasing, so it looks like this. A negative means it's decreasing, and a positive means it's increasing. So we have this basic overall shape. So what is happening at 2 pi thirds? It's a maximum. So I have a relative max at 2 pi over 3. we'll get the corresponding y value in just a second. And at 4 pi over 3, I have a relative min. Okay, is that good for everyone so far? So these are the x values. Sometimes WebAssign will simply ask you for the location, right, like the x value only. If that's what it asked you for, you would be done. If it asked you for the ordered pair, like the actual location in terms of an xy pair, we need the corresponding output value, the y value. So how can I find, we'll start with 2 pi over 3, how can I find the y value of this function at 2 pi over 3? Plug it into the original function, yeah. So this goes back to our original function now, the one up here. And it won't be pretty because part of it is trig and part of it's not, right? Part of it's polynomial, x, and part of it's trig. So I'm not going to end up with a nice, neat little, like 7. It's not going to work like that. Okay, it just won't. So in particular, when I put it into the x, so I'll do it over here. What was my equation? X plus 2 sine x. And I don't know if it's called it f of x or not, but let me do that. We are finding 2/3, 2 pi over 3, excuse me. So 2 pi over 3, that's going to be ugly. Your calculator is not going to help you with this, right? At least not on that part to simplify this. And then I need the sine of 2 pi over 3. Now your calculator might be able to give you the sine of 2 pi over 3 if it's a nice, neat value. If not, your unit circle is a good place to go. So 2 pi over 3 was actually our location right here. I knew that my cosine value was -1/2 there. That's actually why I used that location. What's my sine value there? Square root 3 over 2. And is it positive or negative? It's positive. Sine values are y values, and we're above the x-axis here, so it's positive. So I have positive square root 3 over 2 here. And it doesn't get much more exact and much more kind of ugly than that, really. That's pretty ugly. But that's the y value. Now, if you wanted to get an approximation just to make sure, right, just to double check yourself, you could evaluate that into your calculator, right? You could put x plus 2 sine x into the y1 or the y2. You could plug in the number and you could go with it. Yes, ma'am? Yep, I missed my 2. As soon as I saw you raise your hand, Jewel, I knew I missed something. Thank you. We do need to clean that up. I'm so sorry. There is a 2 there that's canceling. So we'll cancel my 2's. So let's adjust it. 2 pi over 3 plus square root 3. Thank you. Awesome. Okay. Over here, that's the y value. So over here where I was writing down my x and y ordered pairs, right here, I have 2 pi over 3 plus square root 3. That's the y value. And most of the time we are going to keep them exact. We're not going to turn them into decimals. So that's a pretty standard operation. You need to do the same thing at 4 pi over 3. So I have f of 4 pi over 3. So just like before, my x value is 4 pi over 3. I have 2 sine of 4 pi over 3. So from the unit circle perspective over here, that was my location on the third quadrant. What's my sine value right here? Negative square root 3 over 2, right? Yeah. So I have, we'll not lose our 2 this time, negative square root 3 over 2. Like before, the 2's cancel. So the only difference here is that I have, I don't know why this turned into 4 pi over 2. How about I get a 3? 4 pi over 3, and then it'll be minus the square root of 3 instead. So my corresponding output, my y value over here, would be 4 pi over 3 minus square root 3. And then part C says that we want to confirm this with a calculator, right? So if you grab your calculator, I'll sketch what I've got written in my notes since I don't have mine. You're only going from 0, from 0 to 2 pi, right? So make sure that you're thinking about that in terms of your window. And your graph looks something like this, is what I have written down anyway. Maybe a little bit more condensed than that, actually. So the maximum right here is not an absolute maximum. It really is a relative maximum on only the way that this is showing up. And this is happening at the 2 pi over 3. And then I have a minimum happening right here at 4 pi over 3. So that's more or less what my graph ends up looking like. It almost looks like a polynomial or like an x cubed kind of graph on that interval. Of course, it's not quite that clear, but similar idea. Any questions? Let me actually mention one other kind of cool thing your calculator can do to verify that you did it right. So you've got a graph on there, and there's a function in your calculator called max-min. So I'm going to borrow Langley's calculator to remember the actual steps. So if you go in your graph, you just make your window go from 0 to 2 pi if you didn't already to graph it. And I'd like for you to go to second trace. And the trace menu actually has, it says it's calculate menu. And it says value, 0, minimum, maximum. You guys see all that? All those lists? Let's just do maximum together because it'll work the same way if I did minimum. So choose number 4 maximum. And it'll show you back your graph, and now there's a blinking dot, like a cursor showing up. Does everybody see their cursor showing up if you're looking in there? And their maximum is actually the first location that we did. And on the bottom of the screen, it says left bound, question mark. So you'll move your cursor until you get to the left-hand side of the maximum. And once you're over there, you can press enter. And then it'll give you another prompt at the bottom that says right bound, and you move to the right-hand side of the maximum. And you press enter. Anytime it says guess, it really just means you need to be in between those, the left bound and the right bound. But if you want to get close to the maximum, that's fine. Press enter. And it's going to give you a decimal approximation, of course, on bottom. If you want to write that decimal approximation down, you can confirm that over here when we got our maxes and our mins, that decimal approximation matches up to your exact answer by finding your exact answer's decimal approximation. So if you were to write down the ordered pair from here, and then back in your regular screen, you typed in 2 pi over 3, and you got a decimal approximation, which we did that before right here. We think it's about 2.09, right? And if you wanted to type in the 2 pi over 3 plus square root of 3 and get its decimal approximation, it should match that same y values decimal approximation. So it's a great confirmation step. It doesn't give you exact values unless you just happen to have a very nice function. Polynomials it might work for. But in terms of a trig function where it combines some pieces, it's not going to work exceptionally well, but it'll still give you a good idea that you're on the right track.